Let's start. My name is Andrii, and I'm from Ukraine. Currently live in France and Strasbourg, but hope to return back in the future. And now we will talk about the distributed system problems and use Hazelcast as an example of a distributed system. A little bit about me. I'm a software engineer in a core platform in Hazelcast. Also, I'm reading some lectures about distributed systems in National Technical University of Ukraine, and in the past was the organizer of conferences, meetups in Ukraine. Hope that will be in the future we can do the same. And let's start about talking the Hazelcast. And how many of you have heard about Hazelcast? Oh, mostly. And how many of you using Hazelcast or used Hazelcast? Oh, maybe. Oh, so very cool. But maybe the most feature that you are using, it is in Hazelcast, it is distributed in memory data, fast data storage. So it is the basics that Hazelcast, how the Hazelcast has been started. So it implements a distributed map, list, queue, and so on. And it could be used as a caching platform for the databases. But on the top of this distributed data structure, recently we have implemented the real-time stream processing platform that using the core data structure, but provide additional possibilities and additional functionality. For example, you could specify sources of your data stream, specify the logic for the data stream processing, the operation of transformation of the data, and specify the sinks where this transformed data can be saved or processing further. And of course, Hazelcast has a number of different clients on different languages. And to show this how it works in real life, I would like to show a small demo with real-time stream processing, where the real-time stream will be the video that will be taken from my camera, and it will be a face detection demo. And the core logic will be executed into the Hazelcast streaming engine. And now we could see how it works. We will have two clients, Python clients. So yeah, you could see. This is the Python client. And now I will run the Java client. Stop and to run. No, that is cancel. Yeah. Video, this client, yeah. Okay, run. And it is written on Swing because I haven't managed how to run it in JavaFX. So it was the simple Swing application. And with this, we could see that we have, where is the, yeah. So we have the copy of two clients in Hazelcast, in Java and in Python. And you could see the counter. The counter, it is how many times it was the face has been detected. And this counter is saved into the distributed Hazelcast map, and it is the way how you could enrich your stream with some data in memory, and how you could save the state of the stream in a fast storage. We will use this example to describe several issues or problems that we have in Hazelcast for your understanding how the real-time streaming works. And now let's move to the problems. As you know, in Hazelcast, we have our own stack for network primitives. Also, our model for remote procedure call for sync and sync operation. Of course, we have our own concurrency primitives, and now we are working on so-called thread per core engine. It will be another stage in async or programming. And on the top of this, we have built distributed data structure and built the replication mechanism and Raft-based consensus protocol. And of course, we will have a lot of issues in the past, and will have a lot of issues in the future. And on using these issues as an example, we will talk what the problems you could find when you will try to build a distributed system, maybe from the scratch, or analyze some existing distributed systems. We will talk about replication problems, network problems, and don't forget about the clients. And let's start from the replication. And with replication, we will have the following issue. It is about that in some situation, if some of the member or our cluster node has been forcibly terminated, it could lose the data or could lose the state. When it's happened, actually, if we have the job like video processing that I have shown you, it is executed on one of the node, and if this node is failed, the job should continue the execution with the same state on another node, without data loss, without state loss. But in some situation, it could lose the data. Why it's happened? Let's understand why it's happened. It's happened because our job state or snapshot replication is based on our internal, not internal, but public IMAP distributed map implementation. So we are using to replicate the snapshot of our job state, we use our internal IMAP storage. But the problem is that IMAP is eventual consistency data structure. So it is availability partitioning data structure in terms of CAP theorem. And this theorem says that in that case, you could only provide the eventual consistency guarantee. So it is broken, this replication is broken by definition. What we can do to fix this, we should implement some more sophisticated mechanism that I will describe a little bit later. And let's now understand why this IP A and P data structure fails. For example, let's take our cluster with 3 Hazelcast nodes, 1, 2, 3, and take 2 clients. One client write their data. From Hazelcast node 1, it should be backuped or replicated to the Hazelcast node 2. So we have the replication with 2 copies. The first copy is on the main node, and the another copy in some other node. Let it be the Hazelcast node 2. And this data is replicated to the Hazelcast node 2. Acknowledgement is sent to the Hazelcast 1, and then write acknowledgement sent to the client. And if another client would like to read this data, it will be automatically redirected to the main node, that is the owner of those data. It's work in a normal situation, in the best case. But what will happen if during the write operation, Hazelcast node 2 is not responsive or lost the message? In that case, the client will also receive the acknowledgement that data has been saved to the Hazelcast node 1, but this may be some additional error message that if you are not care about, you could ignore it. But the fact that the data from Hazelcast node 1 will be not replicated to the Hazelcast node 2. If after this, the Hazelcast node 1 will fail, the client will be redirected to the backup node for this node, but there will be no data. So in a similar situation, we'll have problems. We will have we have such issue. How we can fix this issue? To fix this issue, we can apply read-write majority approach. For example, Cassandra use it, but it works. It is better than we have now, but there are also the possibility for inconsistency, because read-write majority doesn't guarantee the strong level of consistency. That's why Cassandra has additional implementation of the Paxos consensus protocol that you can use in some particular situation if you would like the strong consistency. In general way, there is the only one way to guarantee the strong consistency if you implement so-called linearizability approach in your distributed system. To implement this, you should implement some of the consensus protocols like Raft, Zab, Paxos. And if you use such data structures that support such consensus protocol, you should be saved during the not all kinds, but majority of failures. Actually, to understand what this protocol and this approach like linearizability demand, you could compare this branch of the tree that is mostly concerned about the distributed system, and this branch. This branch, it is traditional transaction isolation level in classical relational database. So from the bottom, it is read uncommitted, and it will be the fast in a term of performance. And on the top, there is the serializable that is the most slower, yeah, the most slow. But provide additional guarantees for you. The same you could find here in this part of the branch. Those properties like monotonic reads, monotonic writes, your own writes, it could be implemented separately, and it will provide you a good performance, but don't provide you the strict consensus or strong consistency guarantee. The only way to provide the strong consistency is to implement the linearizable approach, but with this approach, your performance will be not the best, and your throughput of your system will not the best as like for eventual consistency. That's why it will be also challenge what you would like be. That your system will be have good performance, or your system have the good predictability. In Hazelcast, we have two kinds of implementation. We have a so-called AP subsystem, and the basic data structure like map, list, queue belong to this. So it is the eventual consistency, and if you would like to build some consistent system on the top of this data structure, it will be the wrong way and the wrong solution. And also we have the CP data structures. It is only the primitive data structure like atomic long, fancied log, countdown, latch, and so on. But for those data structure, we used micro-Raft protocol, that is the consensus protocol. So if you would like to build something consistent, you should use, on the top of Hazelcast, you should use those data structure. Another point and another problem that we faced, it was the network. Let's talk about the network. In Hazelcast, we have our own network model that is not something special. I think that the most distributed system has the same model, but you could describe it. I can describe it in the following slide. We have the outbound queue these packets. What is the packet? Packet, it is a remote procedure call, some operations that is serialized and put it into this outbound queue and will be sent over the network on the another Hazelcast member. There is inbound queue. Inbound queue also collect reading data from the network, deserialize this, and in multiple threads trying to execute commands that another member has been set. With this approach, you could have the following problem. It is the famous tweet that tells that in distributed systems there are only two hard problems. First of them is exactly once delivery. Second, guaranteed order of messages, and exactly once delivery. As you can see, the order is wrong here, and the exactly once delivery duplicated 2 times. If you would like to put your like here, please scan the QR code or retweet it. But it is true, and we have problem, and of course we have problems with both this situation. First of them, it is reordering of messages. With reordering of messages, there was such kind of the issue related to the situation when new member trying to join the existing Hazelcast cluster. Let me describe in detail what it is about. If you have Hazelcast with 2 members and additional member would like to join to the cluster, it sends so-called join request. In this join request, it includes its IP address and unique ID. And it's set in the following while loop. What we can see in this loop? It is while true. It is while max try count. So we trying to send these messages multiple times, and we send these messages join request to all existing nodes until we will have the answer from so-called master node. And we are trying to do it as many times as max try count, or until we receive the response from the master node. So it is so-called busy loop. It is okay, and in most cases it works correctly, but in some cases it could fail. When it's happened and why? Let's describe this model or solution on this diagram. In this diagram, we have 2 Hazelcast nodes. This is IP addresses of those nodes, and Hazelcast node 3 trying to join the cluster. For this, it starts sending the join request with the IP address and unique identifier. So it sends here, and here. And if during this initial joining to the cluster, this Hazelcast member will be restarted, it will be restarted with the same IP address, but with the new unique node identifier. And it's okay, and with this new identifier, it will start sending the join request message with new attributes. And it is okay, and if at this moment this Hazelcast node 3 has successfully joined to the cluster and received the acknowledgement from the master, it will stop sending the join request, and it will be joined to the cluster. But with our networking model, there is possible the following situation, that somewhere in some message queue or somewhere in thread queue could be stuck this old join request message that can reach node 1 after the joining process of updated Hazelcast node tree has been finished. In this case, Hazelcast node 1 will consider this join request as a new request from the new node, and it will remove this new ID node with new ID from the cluster, because it will consider that, oh, we have the new join request. It means that this node go away, and maybe it is restarted, and now we have the new join request. So we have boom. The cluster will be split on several parts and will no longer be connected again. What we can do for this? We should detect and ignore outdated messages. How we can do this? For example, we could use timestamp. In general, it is not recommended to use timestamp because the time difference on different node could produce you different timestamps. And in classical distributed system theory, it is a prohibited way to use the timestamps. But in real life, many systems use it. For example, Cassandra also uses timestamps for detect the last to resolve the collisions. And in Hazelcast, we also in some places use timestamp, but besides timestamps, we also trying to synchronize our clocks from different nodes. So it is not good, but it is possible to use timestamps. The more classical way, it is to use so-called logical clock, vector clock, or Lampert clock. Lampert clock or all kinds of clocks have no connection with real clocks. It is some counter that will be incremented when system state is changes. For example, we could use some version of the cluster and put it into our join request. And if the current cluster state, current cluster version is bigger than the version in a join request, we should ignore such message. Or the third options, we could use, we could hold in memory all disjoint members from all members that has been disjoint from the cluster. And by the way, we have used to fix this issue, we have used the third options, because for those options we should change the message type, and it is changing in API, and it is very hard, and it is not easy operation to do this. So we decided to not harm our system a lot and save all disjoint member in a list. And when we have the join request, we are searching in those lists if we know this UID from this join request. But the downside of this approach is that in theory this list will be always grow, and in some case it is hypothetically, but in some case you should get the out of memory error. And talking about the out of memory error, we also have this kind of errors. And it is related with, as you could imagine, it is related with our outbound queue, our outbound message queue. If we have taken the memory snapshot and analyze this, and in the memory snapshot we have found that our outbound queue take around 2 gigabytes, and inside this queue there are a lot of packets with size about 65, 60 megabytes. What we can do with this? Yeah, something like this. What we can do with this? We could reduce message size because actually we have the limit for the number of messages in a queue, but it is by default it is 1 million messages, and if the message size is big, 1 million of big messages is also brings the out of memory error. In another option, you could implement some rate limiter or back pressure behavior, or apply a drop policy for old and new messages, like in a traditional queues. So you could drop old messages and give the place for the new messages, or you could drop the new messages to save the old messages. So this is your option. And talking about the clients, don't forget that they are also the part of your system. And with the clients, with the CP subsystem, we have the problems with the distributed log. What is the problem about? Hazelcast support distributed log, so if one client takes this log, it will be the owner of this log for a long time. How this process is happen? We have the Hazelcast cluster and we have the client. Client would like to take the log. It could be taken by the following code. So we asked the CP subsystem to get my log, log. Here we implement some logic, and after we have finished, we should call log unlog. But we should guarantee that if the client, for example, failed, this log will not live forever, stay forever in a Hazelcast cluster. For this, every log is supported by heartbeats from the client. So if the client fails, after the some timeout, Hazelcast cluster will automatically call the unlock operation, and another clients could take such log. So for the situation when the clients failed, we have such logic. But what will happen if the cluster has been restarted? And if the cluster has been restarted, we have no such code, no have such options. What will happen in this situation? In this situation, client will continue to send the heartbeats to the Hazelcast cluster, but if the cluster has been restarted, it has no information about the client log. It is not very critical for the cluster, but it will spam its logging system. And for the client side, the client is blocked because it couldn't receive the response for the heartbeats, and all operation on the client that relate on the log also couldn't go further. What will be the solution? The solution should be, don't forget that the client is also part of the distributed system, so you shouldn't I imagine that client should do by their own. If you are responsible for the client driver or for the client code, you should consider all situations that could be happened. And last but not least issue that we have, I will also show the demo. As you can see, it is still in open state. And what is interesting, it was found by one of my students during the practical task related with Hazelcast, and it is related with pessimistic locking behavior. And it is only reproducible, I don't know only or not, but it is reproducible in Python. In Java it is not reproducible. What it is issue about? I will run some Hazelcast test now. So what we no, this one, yeah, I should run, yeah, It is okay. So I am running the cluster and we'll run the code. Now I will explain what this code is doing. In this code, what we are doing, we are using the map log operation, yeah, and for the particular key, we are trying to implement the counter. The counter that for this key holds the value for this counter, and we are running this increment cycle in 10 threads, yeah, in 10 threads. So for this, I'm using even the virtual threads with Project Loom. Cool. If I run this code without the log, that will be the concurrency problem, and you will never get the value, the correct value of the counter. The correct value of the counter should be 5,000 multiplied by 10, so it should be I will show the value. And yeah, we could see that this is the counter value is correct, and this took around 19 seconds. Okay. If we trying to implement the same code in Python, I don't know. Yeah, it is increased. So the basic code will look the same. Yeah. We have the very strange results. The results the results will be correct. The final result will be correct, but the time it is drift from run to run. So I have run it before several times. The usual time it is about 41 seconds, 40 seconds, and so on. But in some cases, it could take several minutes or even several hours. And it is reproducible with Python. I have tested it multiple times with Java client, but with Java client it is okay. So I have the assumption that it is maybe some problems in Python, or maybe some problems in our driver for Hazelcast in Python. So this issue is still in investigation, and I really don't know where is the problem. So you could join, and if you know Python memory model or threading model, you could try to help us with this issue. And finally, the key takeaways for my talk. It is you should know about what problems could the distributed system would have. For this, it is described in such books like Design Data-Intensive Application, Database Internal. The most talks in this room about database and data structure. You could also find these topics inside those books. And in addition, verify your solution or your system or another system that you would like to implement with so-called my bad opinions checklist. It is a very funny checklist where you could point step by step, try to apply it to your system and examine is it applied or not. Most of the problems that I have shown you could be found in those checklists. And distributed system is very hard, and even know all things about them, you in some place could have such kind of errors. And if you would like to know more about not Hazelcast problems, but Hazelcast benefits, you are welcome to join tomorrow talk by Favas, building high-performance real-time stream processing with Hazelcast. And this is all. Дякую за увагу. І давайте переходити до... sorry. Let's start with questions. So, should I refresh? Oh. Or there's no questions? No questions. Okay. So if no questions, thank you. What is the difference between Hazelcast and Kafka? Kafka is more like a messaging system. Hazelcast, it is distributed in-memory data platform. So with Hazelcast, with Kafka stream processing, in theory, you could do the same that with Hazelcast real-time streaming, but with Kafka, it has no, in addition, in-memory distributed map, and it will be, you will require additional in-memory system, for example, Redis, to store the state of your streaming processing. And Kafka is more oriented and more like message streaming, yeah. And Hazelcast, it is more distributed data structure. So it will be better to compare Hazelcast with Redis. So it is more closer than Hazelcast and Kafka. How is it compared with Apache? Ignite. With Apache Ignite, it could be compared in the term of performance. So we have some performance tests, and this test said that for this particular test, Hazelcast is faster than Apache Ignite. But it will be also depend from the test and from data that you are processing. The benefits of the Hazelcast streaming is that you could save data of your state of your stream inside the Hazelcast. For example, we have integration with the Feast framework. Feast framework, it is a framework that helps machine learning, yeah, and that provide feature storage. If you would like to implement some image recognition, for example, for face tracking and so on, you should have a huge database of different features. And if this feature is stored in relational database on a hard drive, it will be very long to query them, but if they saved into the memory, it will be improves the real-time machine learning a lot. And with this combining in-memory distributed data grid with real-time processing platform, we could combine those features and improve the performance of our pipeline. How the future of JCache? I used it without Hazelcast years ago. Actually, as our internal statistics said, we have almost no clients that used JCache. So try to use IMAP storage that could be replaced of JCache. And I don't know in the future. I think I don't know, but it seems that we will not support it in the future because we are not trying to introduce new feature into JCache and more paying attention for distributed map. How are conflicts resolved in Hazelcast? For conflicts resolution for IP subsystem, there are a lot of strategy for conflict resolution. So there are default strategies. For example, you could use timestamp. You could use the last access time. For example, if you have one map and another map, and it contains conflicting data, and the cluster is joined back after the splitting. The part where the data has been accessed most recently will be saved and replace the data with the old access time. But you could also implement your own resolution strategy. You should implement some method called resolve conflict, where will be the one put part of the data and another part of the data with additional metadata, and in the body of this method you can put the logic how to resolve such kind of conflict. So it is very tunable solution for this.